When offline programming is done correctly, you get this: a massive industrial robot operating at top speed, executing complex tasks without a second of hesitation. It saves countless hours on the factory floor. But if the virtual environment doesn't perfectly match the physical reality, the results are expensive. A slight misalignment in your software can lead to hardware crashes, destroyed end effectors, or entire batches of defective parts. To prevent those errors, you need a system. We use a 5-step pre-flight checklist. It's a structured workflow designed to verify every detail of your digital simulation before you export a single line of code. By locking down this virtual workspace piece by piece, you build a digital shield. It catches potential errors on screen, protecting your real-world manufacturing line from costly physical failures. Before we even touch the checklist, we need the right baseline materials. You must have exact digital models for both your specific robot arm and the exact tool you intend to use. Close enough is not good enough here. And before loading those models into RoboDK, check for software updates. This needs to be your very first action. Running an outdated version actively exposes your simulation to unpatched physics calculations and known security vulnerabilities. Updating guarantees your digital environment is operating on the most stable foundation possible. Step 1 is robot calibration. A common trap is assuming the default digital model in the software perfectly mirrors your setup on the factory floor. Physical wear, mounting variations, and slight factory tolerances mean they rarely match out of the box. To fix this, open the RoboDK calibration module. Work through the prompts, using the sliders to align the digital model exactly with your physical robot's known configuration. Once the arm is calibrated, we move to Step 2, configuring the end effector. The tool you attach to the robot dictates how the entire system performs. Look at this diagram. You must input the exact functional dimensions of your specific tool. Guessing or estimating its size throws off your spatial map. You also need to enter the exact weight. A heavy tool directly alters the momentum and physical boundaries of the virtual arm, changing how quickly it can safely stop and turn. Finally, verify the setup visually. Ensure the configured graphic maps flawlessly to the end of your digital robot arm. Locking in these precise physical inputs guarantees the robot knows its true size and weight, preventing it from overshooting a target or missing a weld point during physical execution. Step 3 tackles spatial alignment using reference frames. A reference frame is simply the coordinate system that tells the robot where it is and where the workpiece is located in relation to it. You need to define these axes manually. Carefully snap the X, Y, and Z coordinate axes so the robot space aligns precisely with the coordinate grid of your workpiece. Immediately after adjusting these axes, run a slow, virtual test. This confirms the connection is mathematically sound. This check is critical because misaligned reference frames are statistically the primary cause of severe positioning errors on the factory floor. By synchronizing these coordinate systems, you ensure the spatial rules of your digital workspace flawlessly mirror the layout of the physical factory. Step 4 is path planning. The most common mistake here is building a single, massive program full of convoluted, tangled movement paths. Instead, break the operation down. Actively organize complex tasks into smaller, modular segments within the program tree. To truly optimize these new trajectories, you have to account for specific parameters. Factor in the speed, acceleration, and specific joint limits at each waypoint. Structuring your program with modular, calculated paths makes the code much easier to read. It reduces your debugging time and translates directly into shorter physical production cycles. Step 5 is collision detection. Think of this as the absolute final safety barrier before you export your program to the real machine. A static check only looks at specific waypoints. You need to enable continuous collision checking, forcing the software to monitor the entire sweep of the robot's movement across the full simulation run. If the path intersects with an object, the system flags it. The interface visually pinpoints exactly where the interference occurs. From there, you simply adjust the problematic waypoint or alter your approach speed. You run the check again until the path is completely clear. Taking the time to run this proactive digital checkpoint guarantees the robot will clear its surroundings, eradicating the risk of destroying physical equipment. Run through all 5 steps, and you get an error-free robotic workflow. The machine operates continuously and efficiently because the instructions are perfect. Once you master this checklist, you can look at ways to speed up the process itself. These foundational setup tasks don't always have to be done manually. RoboDK has native Python scripting capabilities. You can write scripts to automatically load tools, configure weights, and align reference frames, cutting out the repetitive manual work entirely. But before you can automate the setup, you have to know exactly what the setup requires. Mastering this strict foundational checklist is the required first step towards achieving total, customized robotic automation.